And we want to make sure we're really good at understanding what a conditional probability is, and really make sure that this is the essential question right here. How do you calculate a conditional probability? Very important to understand that, okay, how to calculate it. So you have to know what it is and how to calculate it. So here we go. The probability that an event, say B, occurs given that a different event, we'll call it A, has already occurred, is called the conditional probability of B given A. And it's written P, B with a vertical line. You remember me talking about that, A. So this is the conditional probability notation, probability of B given A. So here, let's go through and see kind of what that means and how it works. There it says 100 people who have frequently got migraine headaches were chosen to participate in the study of a new anti-headache medicine. Some of the participants were given the medicine, others were not. After 1 week, the participants were asked if they got a headache during the week. The two-way table summarizes the results. So we have these people that were totaled 100. Okay, the data totals 100. So if we add together all these numbers right here, they add up to 100. Now 60 of the people, okay, fall under this category that did not take medicine. This whole column needs to be moved over. I can see this is the took medicine column, and it needs to go right here. So there's some error in this web page, and this is the no medicine right here, and this should be the total column right here. So these three need to be moved over. But 60 then took the medicine, 40 did not take the medicine. So I think I'm going to just try and see if I can fix that. Let me see if I can fix that. Hold on just a second. I'm going to actually just write here, took medicine. I'm going to delete this guy right here. I think I can delete that. And this is did not take medicine. All right. So, and that would be the total over there. I'm not going to rebuild the table, but that's pretty much what it's going to say. Okay, so out of the ones that, and this way we could look at it, there were the ones that got a headache and the ones that did not get a headache. So we had 27 of the 100 that got a headache, 73 who did not. So this is our total column. And when you add together all of them, when they're split as headache or not headache, you add together, it comes to 100. Or as took medicine, did not take, it still comes to 100. So this is what we call a two-way frequency table. We count the frequencies in here, and we split them, and we look at them in two ways, okay? Basically, that's an informal way of looking at what this table says. But we can say one way of looking at it is whether or not they got a headache. That would be looking at it across this direction, right? Another way of looking at it would be whether or not they took medicine, and we'd be looking down to see that direction. And either way, when we come across, we end up that there was 100, no matter how we split it. So that's a two-way table right there. You see it. So it says to the nearest percent, what is the probability the person who took the medicine did not get a headache? So notice the question, the way it's worded. This is so important. A person who took the medicine. We are being told here that a participant took the medicine, and we're talking about a participant who took the medicine. So in other words, we're only looking at this column. Oh boy, not that one. We're only looking at this column right here. These 60 people. That's all we're looking at is the 60 people. So they're asking us, what is the probability that they did not get a headache? So we're looking at how many of these people in this column did not get a headache, and that would be 48, right? And what's the total? Well, we wouldn't go by the total that includes people who didn't take the medicine. We're talking about the total of the people who did take the medicine. So that'd be 48 out of the 60. So let's go through here and answer these questions. It says let event A be the event that a participant took the medicine, and B be the event that they did not get a headache. So to find the probability took the medicine, did not get the headache, you must find the probability of B that they did not get a headache given A that they did take the medicine. You're only concerned with participants who took the medicine, so look at the data in this column only, took medicine column only. So there were 60 participants who took the medicine. Of these participants, 48 did not get a headache. So the probability of B given A. Okay, so what we're going to do is we're going to put in B given A, which is 48. So the 48 over the 60, which of course you could write is equal to, and we reduce those, and I happen to know those both are multiples of 12. 12 times 4 is 48, and 12 times 5 is 60. I just happen to know that, but you could use your calculator to find the same. So that's the probability of B given A. So to the and it says to the nearest percent, well, you'd use your calculator, but I know that that is 80%. Okay? Next part, to the nearest percent, what is the probability that a participant who did not get a headache took the medicine? Aha, so they're asking us about participants who did not get a headache. So this is now the probability of A given B. So let's go here. So the probability of A that a participant who did not get a headache, so we're looking at these people here, and that's 73, took the medicine. That'd be the 48. So we're going to go down here. There were 73 participants who did not get a headache. Of these, 48 took the medicine. So the probability would be 48 over 73. Well, I know that percentage is not very good, but I will, and I don't want to do that one in my head. I'm not that good. 48 divided by 73 equals, and I'm getting about 66%. It says to the nearest percent, so we'll say about 66%. Okay? In general, do you think the probability of B given A is equal to the probability of A given B? Why or why not? So this goes to what we're going to get into here in a little bit, which is, it gets into the idea of independence. The idea of independence. So what we're saying is, do you think the probability that a person who took a medicine, or the person who did not get a headache, was a person who took the medicine? So B given A was did not. Here it is. B given A is this one. No, A given B is this one. Sorry. So they did not get a headache, took the medicine, and they were supposed to compare that to B given A, which is that a participant who took the medicine did not get a headache. So in general, do we think they're equal? Well, they're clearly not equal. They're clearly not equal. Why is that? There's a better chance that if they didn't get a headache, that if they took the medicine, they had a better chance to not get a headache. So if they took the medicine, they had a better chance to not get the headache. And I would also say this: 2/3 of the people who didn't get the headache took the medicine, right? 2/3 of the people, about 2/3, 66%, who did not get a headache took the medicine. Okay, and so we would add that in, and if they didn't get a headache, they more likely, right, we'd say 2/3 of them did take the medicine. So what would this lead us to think? It would lead us to think that maybe the medicine was effective, right? Maybe we had some effective medicine because, look at the probability that now of the ones that got a headache, it was much more likely that if they got a headache that they did not take the medicine, and if they did get a headache that they did not take the medicine, and it is more likely that if they did not get the headache, that they did take the medicine. Okay, I know I've talked that around, but I hope you can see that. So how can you use set notation to represent the event that a participant took the medicine and did not get a headache? So they took the medicine, we called that A, and they did not get a headache, we called that B. So that a participant took the medicine and did not get a headache. Well, that would be the, actually I can't really write that very well. I have to maybe draw it. See if I can draw it real quick. So I would say event A, that they took the medicine, and event B, they did not get the headache, and this is an and. And is intersection. We're looking for the intersection. And remember, just like a business partner, you both have to be present. So we're not counting people who just took the medicine. We're not counting people who just got a headache. We're looking at both. So that would be the notation that we'd use. Okay? All right, we're going to keep moving on here. So let's see. We're going to develop a formula for conditional probability. Oh, let's see. How can you use set notation? Okay, I finished writing that. The probability that a participant took the medicine and did not get a headache equal to either of the conditional probabilities that you calculated in the example. Aha, so that's a question here. Is the probability they took the medicine and did not get the headache equal to the others? Well, that would be 48 over 100. And so our answer is 48% that took the medicine and did not get a headache. So now the question would be, why would it be different, right? Why is it different? Well, because we are including people who didn't take the medicine. Or basically removing the conditions. So that's what's going on there. So basically, you know, here we come down here, and this is to get to the formula. And man, this is just goofy, isn't it? I'm so sorry. Event A is there. This sucker should go here. Well, I can tell that there's something wrong with this table here. So I'm going to paste it there. We know that's B. Right? And then over here, sorry, we're just going to put that in there. Matter of fact, let me pause this and I'll try and fix it up real quick, and then we can talk about it. Okay? Oh, here we go. Pause. Okay, sorry about that. And the color's not fixed, and it's a little goofy, but this represents event B. They did not get a headache. And event A is really this one. They took, oh, still got another fix to do. So sorry. Okay, I'm so sorry. We should have the table. I wish it was better, and it's just not, and I'm sorry. This one here is event A. Okay? This one here is event B. Okay? The number in A is 60. That's the number of people who took medicine. The number in B is 73, the ones that did not get a headache. So here we go. You can generalize your work from the previous example to develop a formula. Recall how you calculated probability of B given A. Okay, you found that the probability of B given A was equal to, so what did we do there? We say B given A was equal to, well, we're only looking at the A's. We're only looking at the A's, so it was 48 out of 60, right? When it's B given A, so we're only looking at the A's, so it's out of 60, and it's 48. It says, use the table shown here to help you write this quotient in terms of events A and B. Okay, so we're going to write that out. So we would say the probability of B given A is equal to the probability of, and it's A, oh boy, I'm going to put an N there to represent intersection. A intersection of B, okay, divided by the number of A. I'm sorry, and I should say not the probability of A, it's the number of A. It's this is what should be there. Actually, maybe I can just, let's see if I can copy that and then paste it here. That'd be good. There we go. Divided by the number of A, right there, that term. So now you can see there's pretty much our formula. The number in the intersection divided by the number of A's. Okay. Now divide the numerator and denominator of the quotient by the n of S, the number of outcomes in the sample space. This converts the counts to probability. Okay. Oh boy. Okay. Hold on just a second. All right. So what I'm doing, just copy this down and paste it here. Okay. And what we're going to do is we're going to say, we're going to copy that there and do divided by n of S over n of A divided by, okay, n of S. So basically our numerator becomes the probability of the intersection, 48 over 100, divided by the probability that they took medicine, which is 60 over 100. Okay? That's where that goes. So write a formula for P of A. Sorry. Probability of A given B in terms of the number in the intersection and the number in B. So we would say the probability of A given B, Control C, I put that down there. I'm going to put it like this because I know I'm going to use up some room. Probability of A given B is equal to, where's my equal to? All right, now I'm going to do this numerator and then denominator. So the numerator is this. Sorry. Divided by the denominator, which was n of B. Sorry. Again, it's just the same exact process. In fact, I'm spending too much time walking through this even. It's the same exact process that we would first start out by doing this, and then we would turn it into the probability. Okay? Instead of n, we would divide by the number of S, and then we're talking about the probability of the intersection over the probability of B. So that's really how that's happening. I'm going to try and clean this up and wrap this up. Just a second. Okay, I'm going to start using the pen a little bit more because I think it might work a little bit better. So here we have the probability of B given A. This is the actual, this is very important here. This is the actual formula in here, and it's the rule that you need to know. The conditional probability of B given A, the probability that event B occurs given that event A occurs, is given by the following formula. The probability of the intersection of A and B, so where they overlap, just the overlapping part of those two subsets, and then those two sets rather, and then that is divided by the probability of event A occurring. Okay, so the probability of the intersection over the probability of just A, and that's for considering that we're only dealing with A. This is B given A. So in this case, it's very critical to remember that A is given, that this is the part that for sure happened, and now we're predicting what the probability for B would be. So that's why A goes down there in the denominator, because that's really all we can look at that's going to happen. We're told that A is going to happen. Okay, let's work through a little bit more here. In a standard deck of playing cards, find the probability that a red card is a queen. So in this case, they're telling us that it is a red card. So the given is that it's a red card. Okay? And they're saying that Q is the event that it is a queen. So So we're finding the probability of the queen given that it is a red card. So find the probability that it's a queen when you know that it's a red card. So there are how many red queens in a deck of 52? Well, there's going to be 2 red queens. Okay? There's going to be a queen of hearts and a queen of diamonds. So the probability of that is 2 over, it would be like this, 2 over 52 or 1 over 26. Okay? And then there are how many red cards in the deck? There are 26 cards in the deck. So the probability of red is equal to 26 over 52 or 1/2. So using the formula for conditional probability, okay, so we're saying if we're going to use that formula for conditional probability there, the probability of Q given R is going to be the probability of the intersection of Q and R over the probability of R. So that's 1 over 26 divided by, all right, 1 over 2. Okay? 1 over 26 divided by 1 over 2. So let's do that. I get this marker here. 1 over 26, right? That's the intersection's probability divided by 1 over 2. Well, we don't like that, man. Right? We don't like that. So what are we going to do here? Well, with compound fractions, we can just write them out. 1 over 26 is divided by, we write them like this, 1 over 2. And then to solve this, we would inverse and multiply. So 1 over 26 times 2 over 1. And that's going to work out to be 2 over 26. Or 1 over 13. Okay, that's how that's done. We found the probability of the intersection. Okay, there are exactly 2 red queens, and divided it by the probability that it was red. And that gave us the probability, or what we call the conditional probability. If we know that it's red, given that it's red, here it was, given that it was red, what was the probability that it was a queen? That was 1 over 13. All right, and let's just see. We do one more of this practice here because these are really good to see, and you need to have like a really good idea about these. Now these columns are goofy again. This should say these are the passed exams, these are the failed exams. In fact, I can fix that. So here's our passed exams, our failed exams. These are our passed exams. Okay? They got less or more than. So to the nearest percent, what is the probability that a student who failed the exam got less than 6 hours of sleep? So if they failed, it says that a student who failed the exam, so this is our given. Notice the given, the language that's used to indicate that it's given. It says that A, and then a qualifier tells it this, and then it goes into the next one. Got that. So the given was a student who failed the exam. So we're only looking at the students who failed the exam. Okay? And now we're going to see what is the probability they got 6 hours of sleep. So they got less than 6 hours. That would be this one. We're looking at this number here. So now we try to figure it out. It's the probability of the, I'm going to just do this in shorthand, the probability of the intersection over the probability of the given. So what was the given? Well, there were 18 given out of 120. So probability of the given is equal to 18 out of 120. I know 12 goes into both of these. Let's see, 18. Does 18 go into both of these? Well, let's see. I can divide 6 into both of these. I get 3/20. So we'll just call that 3/20 if I divide top and bottom. So the probability of the given is 3/20, and the probability of the intersection is 1/12. It's 10 over 120. That's the probability. That's this one right here. So we need to take that and divide it by 3/20, which means 2. And by the way, this cancels. So we end up with 1/12 times 20 over 3. And we end up with, I can reduce this. This will be 6, and this will be 10. But my answer is going to be 10 over 18. That's going to be my probability there. 10 over 18. And if I use my calculator, which I am trying to turn it on right now, 10 divided by 18 equals, oh boy, Control Enter, approximately 56%. So that is approx. Oh, it's to the nearest percent anyway. It asked me that, so 56%. That's to the nearest percent because I had to round up a little bit. All right, so that's how that's done. You see, I'm not going to go through all the rest of these, but they're good for you to know, and we've got a lot to show you about independence versus dependence.